Hello everybody. In this video we're gonna solve a couple of examples or a couple of problems just to apply what we learned in the previous video about the concepts or the terms of the concentrations and the ideal gas law and these kind of things. So the first example is about air. We know that air is composed of oxygen and nitrogen. The mole fraction of oxygen is 21%, of nitrogen is 79%. And in this problem, we're asked to find the mass fraction of both oxygen and nitrogen. This is the first requirement, and the second is to get the mean or average molecular weight of air. We know that the temperature is 25 degrees Celsius and the pressure is 1 atmosphere, and we know the molecular weights of both oxygen and nitrogen in kilogram per mole, which is gonna be 32 gram per mole for oxygen and 28 gram per mole for nitrogen. So this is a very simple, straightforward problem. So in this case, we will only, we'll first go for the first requirement, which is the mass fraction. And as we said, we start with the definition. So for the mass fraction, it is the mass divided by the total mass, which I can put in the terms of number of moles and the molecular weight. And if I divide up and down by the total number of moles, I'm gonna end up with the mole fractions. So this is the information that I have. So from this I can get the mass fraction of oxygen, and the same for nitrogen. So see, it's not exactly, of course it's not going to be the same value, but it's higher for oxygen because the molecular weight of oxygen is higher than that of nitrogen. So the mass is going to be higher. So the mass fraction is going to be higher for oxygen. The second requirement is the average molecular weight, and the average molecular weight, as we said, is the summation of mole fraction multiplied by the molecular weight, which, by the way, is gonna be this denominator here. This is the same thing that we have here. It's the denominator, which is gonna be 0.0288, and that's why we always, or in most of the cases, put the molecular weight of air as 29 grams per mole because of this average molecular weight. For the second example, we have a mixture of three components: hydrogen, carbon dioxide, and methane, and we have the mole fraction 50%, 40%, and 10%. These are the percents by volume, which is the same as by moles. So this is the mole fraction. The temperature is 400 degrees Celsius and the pressure is 1 atmosphere. And we need to determine the molar concentration and the mass fraction of each species of the mixture, as well as the density of the mixture. So there will be parts that are very similar to the previous example. The mass fractions, we know the mole fractions, and we can get the mass fractions of this. This is going to be one part of it. And the density of the mixture is going to be kind of related. But let's start with the first thing, which is the molar concentration. We know that the molar concentration has the units of moles per meter cube or per unit volume. So this is gonna be N over V, and since we are dealing with a gas, so this is a gas mixture, the pressure is not very high, it's 1.5 atmosphere, so we can apply the ideal gas law. So in this case, the N over V equals P over RT, which is the total number of moles. We will substitute for the pressure by 1.5 atmospheres. In this case, we must make sure that the units of R is suitable or is homogeneous with the units of the pressure. We use 0.082 because it has the units of liter, atmosphere per mole Kelvin. But for other values, if I use 8.314, then it's gonna be in Pascal meter cube per mole Kelvin. And in such case, if I substitute here by with 8.314, then I have to put this as atmosphere. So I have to multiply it by the 1.013 multiplied by 10 power 5. Just to make sure that the units are homogeneous. So this is going to be the concentration, and the units will be mole per liter because, again, this is gram liter multiplied by atmosphere divided by mole Kelvin. So the volume is in liter, and the number or the moles is in gram moles or in moles. So this is the total concentration. I want to get the molar concentration of each one of them. So it's gonna be Y multiplied by C. So this is gonna be Y hydrogen multiplied by the total concentration. In this case, this is hydrogen, the same for carbon dioxide, and the same for methane. So these are the three. And of course, the summation of these three must be equal to this value here. So it's the like one way to check on the numbers. The second requirement is to get the mass fraction. This is going to be the same as before. So it's going to be the Y multiplied by M divided by the summation of Y multiplied by M. It's going to be 0.049 for hydrogen, the same for carbon dioxide, and the same for methane. And this is kind of thing that is like a point that we need to stop and take a look at. The hydrogen represented 50% by moles, but it represents less than 5% by mass. And again, if you take a look at the molecular weights, it's 2 compared to 44 and 16. So the carbon dioxide, which was 40%, represents 87% of the mass that we have, while the 50% hydrogen represents only less than 5% of the weight. So this is, or the weight, yeah, the total weight. So this is something that's important to keep in mind. The last thing is to get the average molecular weight, and we can get the average molecular weight from the ideal gas law by putting the equation in the form of Pm equals rho RT. So this is how we can get the average, I'm sorry, the average density. So this is the average density. Where we will apply the law. We just need the average molecular weight, and again the average molecular weight can be got from the same way, and then we can get the average density of the mixture. So this is how we can do it. There is one other option that we can do, which is gonna be like a nice alternative, is to use the relation between the density and the molar concentration. So we know from before that I'm sorry, that the total concentration of the mixture is this. So if we divide this by the average molecular weight, so we have to calculate the average molecular weight anyways, but if we divide the molar concentration by the average molecular weight, since you have already calculated it from the ideal gas law, it must give the same value as this. So this is the last requirement in this problem. In the next video, we will continue the terms and the terminology of the or some of the basic concepts that we need to understand and grasp well, that we need for like the applications of mass transfer. So I'll see you then, inshallah. Goodbye.